Okay, so on Friday we finished up a lead control example, and then we just barely started a lag control example. And so we said that, so lead, kind of draw some analogies here. Lead control is analogous to PD control, and lag control is analogous to PI control. The homework this week on the last problem asked about lead lag control. There's no mystery to what lead lag control is. It's basically a lead concatenated with a lag controller. All right, so I just wanted to inject that really quick. First, this will be kind of an aside note. If you want to have lead lag. All right, so our lead controller, we said, is of this form. All right. And then the constraint is that the 0 is less than the pole for lead. Our lag controller, say this is lead, exactly the same form. But then pole is less than 0. All right, so they're exactly the same form. They are just you're interchanging which one's less, the pole or the 0. So a lead lag controller is just these two multiplied with each other, and you're going to have, and if I were to throw these all in one, I can lump the gains together. Instead of having two redundant ZCs and PCs, I can have, say, Z1, P1, S plus Z2, S plus P2, and then apply the constraints. Whoops, didn't want to do that. All right, so this would be the lead lag, and I just apply the constraints that the dynamics of the lag are always slower than the dynamics of the lead. So we would have then that P1 is less than Z1, is less than Z2, is less than P2. All right, so that would be lead lag. So no real mystery to it, and I think this hopefully should come through in the example we did today about basically the order in which you design these, but this is the basic form here. All right, so then the question on problem 3 of this homework is asking you, show in the frequency domain how the lead lag controller approximates a PID controller. And it gives you the Bodie plot for a PID controller, and then you're showing how this approximates it. So it's more of a conceptual problem. It's also going back to some content from 3260 in terms of looking at the action of poles and zeros in the frequency domain, but it was clear I was going to get to lead lag, so I wanted to address this really quickly. There's no real mystery around it. I just want to make sure everyone's aware of what the form is. Okay. All right. So on Friday's class, we just barely introduced the lag control. As we said, that the 0 is greater than the pole, which is the opposite of lead control. So we have this constraint here if we're only talking about lag control. So just like the lead controller, we have a real 0 and a real pole added to the system, and just we flip the order in terms of which one's farther left in the complex plane with the lag control. We will oftentimes, in the lead control example we did, this was always the most convenient form, where we have the S plus then the 0, S plus the pole location. In lag control, it's actually going to be a little bit more convenient to use a different form. I hope this comes through clearly in the example, why this is going to be the more convenient form. The more convenient form is that we have G1 lag is equal to what we just wrote before. K, S plus ZC, S plus PC. We can rewrite this by pulling out the 0 and the pole from the numerator and denominator. And so this would give us K ZC over PC S over ZC plus 1 S over PC plus 1. Or if we wanted to, we could just now lump what we've pulled out in front is just all constants. So we could just lump this and call this, all right, let's just call this another K. It's just another gain in our system. Right? They're all constants, right? And then if we say, instead of designing the system such we have an independent gain K, 0 location ZC, and pole location PC, what's going to be most convenient for us in here is actually looking and saying, we are going to make the pole location some multiple of the 0 location. And so the way in which we do this, and also we're going to constrain the gain as well, but the way in which we write this is we say that it has some gain alpha on the system, it has a 0 location at 1 over t, and it has a pole location at 1 over alpha t. Okay, so what we've done actually is taken this lag control, and instead of having 3 degrees of freedom, we're going to have just 1 degree of freedom. And I hope this may not make sense why we're reducing the complexity of this just yet, but I hope the example will help show why we're doing this. Okay, so we're just basically saying, instead of having PC and ZC as independent variables, we're going to make sure that these have an alpha relationship, such that the 0 location is alpha times farther away than the pole location. So we're doing constraint, and we're just looking at the ratio of the two. Any questions on that idea? Yes? Yeah, it may make sense actually when I get to the Bodhi plot. I hope we'll circle back on this and see if it helps. So just like the generic formulation, all 3 variables are independent, but it's going to be most convenient in terms of design to have them be constrained. So we just have a single design variable to assume. Okay. So we said that. It's approximation of PI control, so it makes sense to compare PI control and lag in frequency domain. So if we look at PI control, just going back a slide. So this would be PI control. It has a 0. The 0 is at 1 over t, and has a pole at the origin. And then, of course, has a gain on the system. All right. So going back to what we know about plotting Bodhi plots, we know that a system that has a pole at the origin is going to have a negative 20 dB per decade slope the entire way. So if we just say this is the point 0 decibels, 10 to the 0 or 1 frequency, and we have 20 dB per decade slope, then we would have a slope coming from the 0, so the pole at the origin. We'd have this contribution, and then we'd have a contribution from the 0 at 1 over t. Right, which then is going to add 20 dB per decade, so it's going to bend then the plot up. So if we look at the total, sorry, I'll draw the phase as well. So we have negative 90 degrees per decade, or negative 90 degrees for all frequencies because of the pole at the origin, plus then an increase in phase from 0 to 90, or it's from negative 90 to 0, centered about the 1 over t. So then the total response looks like this. All right, so this would be the Bodie plots for PI. So that's PI control. All right, so it's just, just really quick, this has a gain at very, very low frequency, right? So if this is 10 to 0, I put the other x at the spark surface, 10 to -1, 10 to -2, right? If I keep on going to lower frequencies, then it's infinite gain for PI control. Yes, Carson.
Graphically, what's the equivalent of increasing the high term with the lag controller?
So, can you repeat that?
Graphically, what's the equivalent of increasing the high terms? Is like moving the both the zeros further apart, or moving to the left or the right?
Yeah, so let's take a look at that. So if we look at this, okay, so here's a transfer function for PI control, right? And so if we, this is the easiest way to look at in terms of a Bodie plot, right? So if we say K is equal to Ki, right, it's increasing the entire gain of the system. And it's also moving, if you increase Ki, that means that T is getting smaller, right? Which actually means that your 0 is moving smaller, 0 is moving to the right, right? Your 0 is at 1 over T. Smaller, yeah.
So towards the imaginary axis?
I was talking about in terms of the Bodie plot, it's moving to the right. Sorry, I can't think this morning. This is getting, so T is getting smaller, right? That means that the 0 is at 1 over T, so it's actually getting larger. All right. So yeah, so it's moving to the right in terms of larger frequency, in terms of where the 0 break is. So you can imagine this plot moves up, and in the position of where this break point is, it moves to the right. Yeah, it's going higher now. Yes?
Why is the break point at 1 over tau or 1 over t?
So if we look at the 0 is the value of s such that this is equal to, such that the numerator is equal to 0. So s is equal to negative 1 over t. That's the 0 point. Okay, so we usually, this is just rewriting a different form, and I hope this becomes clear in a little bit why we're doing this. But usually we talk about the coefficient being on the s to the 0 term, but here is on the s term.
So it breaks at the 0 point?
Yeah, so that's when we get a positive 20 dB per decade component. All right. Okay. So the reason why we write the lag controller in this form is if we look at what happens at high frequencies. So if we look at high frequencies, we're talking about then S being a large number at high frequencies, or if we insert j omega into this, j omega being a large number, then if we say, all right, this is a large number, that means large number, Ts, compared to 1, the 1's inconsequential. Same thing with here as well. So this term is inconsequential, and so we say large number over large number, it's alpha Ts over alpha Ts is equal to 1. Right? So as omega goes to infinity, the magnitude of G1 of lag for this particular design, when we parameterize it in this way, this goes to 1. And so when we get into this lag design, we'll see that the lag design is always done at low frequency. And so what this is saying is we're designing it such that the action of the lag controller has no effect at the higher frequencies, which is usually where the transients are. That's when abrupt transitions in our signal happen. All right, so anything that's low frequency, like a reference signal that's constant, if you look at PI control, allows you to hold a constant position, then it's active. And then at higher frequencies, when dynamic motions are happening, where you care about overshoot, rise time, all those things, it really has no effect at higher frequencies. So what we're doing is we are designing and I think I want to change my plot a little bit here because this is not going to make the argument I really wanted here. I'm going to move this intersection. This should have been here. This should have been 0 decibels. All right. Okay, so if we look at what's happening with the lag control, it has a lag controller has a pole at 1 over alpha tau. So this would be 1 over alpha tau. And that's because the pole is going to now break down at negative 20 dB per decade. It has a 0 at tau. So it's not going to follow this line. If we look at and evaluate this as frequencies very, very small, so as frequencies go to 0, the gain of G1 lag goes to alpha. All right, so what it's doing is it's imparting at low frequencies a gain of alpha. This is, of course, in decibels. All right, so it doesn't have infinite gain at low frequencies like a PI control. It has a finite gain of alpha at low frequencies. Looking at the the phase response of the system. Carrying this down. All right, so we're going to have going from 0 to negative 90, centered about this frequency. So this is going to have this behavior. And then the 0 is going to take over, and that's going to back up to 90. So the total phase response is going to look something like this. All right, so at high frequencies, the PI control and the lag control are almost identical. At low frequencies, they have slight deviations from them. So why did we call lead controller a lead controller? What was the reason for that? Remember back to that lecture? Was the phase positive or negative in a lead controller? Positive. Okay, so it was a phase lead. If you talk about a positive phase, you have a phase lead. All right, that's why we call it a lead controller. And here we see that the phase is negative, which is a phase lag. So if you ever have difficulty remembering the two, just think about how it behaves in terms of frequency. So this is our phase lag. That's going to be this amount. All right. Any question about that before we get into an example on this? Jackson, so your question, remember your question was? I guess it's fine to address it.
It is just about like the alpha. Like I was kind of confused about like the alpha that's versus alpha that's not.
Okay. So the reason why we write it in this form is it's going to be advantageous for the examples to have this property that the magnitude is 1 at high frequencies and then the magnitude is alpha at low frequencies. Right? And so then it's just evaluating the numerator and denominator to determine what values of s make each of them 0, right, to get the 0 in the pole location. Okay, I think this example should clear this up a little bit. All right, so the lag control basic procedure that you'll be using. All right, there's a step 0 in this one. So given a closed loop system with a sufficient transient response. Okay, so what does this mean? This will take some explaining here. The example that we're going to show will have a system with a sufficient transient response already. So you're just given a system, proportional controller gives you a sufficient transient response. That's obviously not always the case, right? So we looked at lead control to improve transient responses of systems, like for instance, overshoot, rise time, settling time, etc. So this means before you get to lag design example or lag design, you actually have to do some work to make sure that the transient response is appropriate. It's meeting specifications. All right, so those of you who have come to office hours or to my office to ask about the project, to say, well, what can we do right now? It seems like we haven't learned lag control, and I've said, okay, you can actually do the lead control portion of this already. We've learned everything you need to know to do the lead control. This is the reason why we're looking at designing lead and lag controllers in a separable manner, actually, where you can do lead control first, and then throw lag control on the end to improve your steady state response. All right, so given that you've done the work to make sure that the transient response is satisfied for your system, then you can jump into step 1 of lag control. This is design alpha to meet the E final specifications. Okay, so this is going to be using a lot of lecture content from, I believe it was lecture 12, which is looking at steady state error of systems. So we're going to leverage all the information, and then we're going to design T, and this is going to be a very wishy-washy statement, which we'll go through some examples showing how this would actually be done, such that the lag control has little to no effect on the stability and transient response. Okay, so step 0 means get a transient response you find to be favorable, right? Depending on what your boss said or whatever you wanted as a design objective. We're going to ensure that we're going to meet E final specifications, and then we're going to make sure that the pole and 0 locations are in a place such that we do not affect all the hard work you did with the transient response and getting that to be appropriate first. Okay. So the reason why we can do that is we have designed, the way we've done this, we have made, what is going on here? Yellow, that's not going to show up. Okay, what setting did I inadvertently change? There we go. Too large still. Okay, so we've made a system, or constrained the system such that the magnitude at higher frequencies is equal to 1. So everything that we're going to do here, in terms of lag control, we're designing how the system behaves at low frequencies or at what we'd say steady state, right? So this has a phase of magnitude of 1 at high frequencies. It has a phase of 0 at high frequencies. So we're going to make sure that all the dynamics of the lag controller are all at low frequencies, so they don't affect the higher frequency contacts, which is how transient response is affected. All right, so we're separating the two designs in the frequency domain, essentially. Okay, so I think an example, that's a lot of me talking. I think an example is probably the best way to go about this. So this example is coming from wind tunnel data. This is from an old book. It's basically wind tunnel data from F-16 that was taken in 1979, and then the data was declassified since then. So it's I don't know, it's a 10-year-old textbook, maybe 15-year-old textbook, but it's from really old data that is now allowed to be out And so it's wind tunnel data, and what it's doing is it's relating the pitch angle, I believe. Yeah, pitch rate. So the pitch rate, this is my airplane flying, this is the rate at which I pitch up and down. It's relating the pitch rate to the elevator angle, and it has this complex transfer function here. So the actual values of this are going to be important for calculations, but the fact that this is a mess of a lot of poles and zeros is not going to actually make our life all that much more difficult. And I hope you'll see that when we go through this example. But this is coming from actual data from tests that people have done before. So the goal here is design a pitch rate controller such that the rise time is less than 0.6 seconds, overshoot is less than 20%, and E final to a step reference or step signal is less than 1. Okay, so these are what your bosses tasked you with doing. So when we say controller, it means that we're putting this in some sort of feedback loop, right? And so what we're going to first start off doing is say, okay, this is our nominal system. This is our plant, right? So what we're trying to control is this F-16. Let's first just see how we are doing from the perspective of, are we anywhere close to meeting our design objectives for control here? So we can do that by analyzing this in software first. So we have two zeros, they're at -10, and they're at -1.029. We have then 4 poles, -10.38, -20.13, and then -0.8957, plus 1.152i, -0.8957, minus 1.152i. And then if we look at the system, it has a gain out front of 203.2. All right, so let's just quickly compare, make sure I type this in correctly. Okay, looks good. That's new. What is this? Experience a low-level graphics error. It may not have drawn correctly. And there's nothing here, so you're right. It may not have drawn correctly. Okay. First rule of computers, you just restart it, right? There we go. So good at my job. All right. Okay. So if we look at the response here, we said that we wanted a rise time of 0.6 seconds. So we see that we're easily satisfying that. So we can start to plot things on here to understand whether or not we're sufficient here. Final value, this is MATLAB's worst function. It doesn't actually allow you to, it doesn't identify what the final value is for you for some reason. I don't know why that's beyond the programming skills of the engineers at MATLAB, but it won't do it for you. So the final value is approximately 0.82 right now. We have a rise time constraint of 0.6 seconds, and then overshoot constraint of 20% on this. And then no settling time given. I'll just make it 5 so it doesn't change the axes of my plot at all. All right, and it did change the axis. Oh, never mind. So what it's showing here is that this would be our this would be our constraint for basically for rise time and overshoot, and we see that our response in terms of step response is within this bound the entire way. Okay. So this was an example where step 0 was satisfied already, so I could get to the actual example of interest, which is lag control. This obviously would not always be the case, and this will not be the case in your project, part 3. All right, so you'll have to do some work designing a lead controller. Yes. So the requirements was rise time of 0.6, right? So this is the line at 0.6, showing that the system should have risen to its new value, right? Rise time is the time at which it takes for the response to first reach our new steady state value, which is C final. So that happens in about 0.2 seconds, probably, right? And then it says overshoot of less than 20%. And then these bounds are an overshoot, this upper bound is an overshoot of 20%. And so the response is entirely within that bound. Okay, so transiently, this is fine. Now the deficiency here is at the problem statement. Go back to that. So the E final to a step reference should be less than 1%. All right, so if we look at our response of our system, right now, a step reference, that'd be a unit step reference, if I didn't add that. Yeah, I should probably add some more detail to that. You see it settles out at 0.82 about, so it's actually somewhere around 18% for the steady state value. So the desired pitch rate, we're not actually hitting it at steady state. We're somewhere off. We're about 18% off. We want to be at 1%. That's that specification. Yes? Oh, so I'm just looking, so it's a unit reference, right? So it should be at 1. And I'm looking at where this ultimately settles out to, and this is just me eyeballing it.
Oh, so you just picked it before by looking at the step response.
Yeah. So this is at 0.82, so it's 18% off. Right? Yes?
Can you make it specific value for our?
Could we?
Yeah.
So yes, we could. I don't know if the step response command and this GUI will do that for us. I haven't looked into that, but this is a linear system, right? So if we're 1% off for a step response of 1, we're going to be 1% off for a step response of 2. So say instead of being 0.01 off, right, we're going to be 0.02 off for a step response of 2. So it should all scale linearly then. Okay. All right, so transiently we have, in terms of steps, we have step 0 is A-OK, right? Okay, so this is kind of the text that describes that here. So this basically says that both of these are met without modifying the controller, and so I'm saying not modifying the controller. The default is just a proportional gain of 1, and so that for this problem just so happens to give a sufficient response. Where we're insufficient is E final, so we need to fix this. And so step 0 is good, right? We don't have to modify step 0 at all. So step 1, design alpha to meet E final specifications. So this is going back to lecture 12. And so if you go back to the notes from lecture 12, we talked about how we can evaluate the final error, and that used the final value theorem. So if we said that we have an open loop system All right, so we have open loop system, which means that we have reference coming in, controller, plant, and then this feeds back, right? So the open loop system is just G1, G2. So open loop means if we were to say somehow cut this cord, right? Cut the feedback signal. So the open loop system is G1, G2. We can always parameterize this as its numerator, denominator, and then the number of free integrators in the system, or number of poles at the origin if we want to. And so then lecture 12, it's been a while since we talked about that. If it's a type 0 system, P is 0. If it's a type 1 system, P is 1, type 2, P is 2, on and on, right? If that rings a bell. Okay. And so what do we have here? What's our system type for this example right now? If we go back, show the transfer function. Zero, 1, 2, 3. 3? 0, 0. So 0 is the number of poles at the origin of our system. Okay. So we have all our poles were given at -10, -20, and then these complex conjugate poles. So for this example, P is equal to 0. So type 0 system for this particular example. And so going from lecture 12, which we had this chart, which then looked at E final. E final is equal to this polynomial A evaluated at 0 over polynomial A evaluated at 0 plus B evaluated at 0. Okay. All right, so what we're proposing to do here is to add a lag controller to our system, right? And so our lag controller is going to be of the form alpha TS over alpha TS plus 1. Okay, so when we're concatenating G2, which is our plant, that's fixed, with our controller, which now we have design flexibility, that we can choose specifically what alpha is, we can then calculate then what G1, G2 would be. All right, so if we say that G1, G2 for a lag control design, it's going to be equal to alpha TS plus 1. Oops, this is out front. Alpha TS plus 1, alpha TS plus 1 in the denominator. And G2 is going to be this long expression. Which is equal to this. All right. So A is in the denominator, B is in the numerator. If I want to evaluate what E final is, All right, so that's going to be this term when s is equal to 0. So if I look at the denominator, right, so in the denominator I have a 1 coming from this term. I have then a 10.38, 20.13, and then this whole term is plus or minus. If we look at, I forget what that actually is. I guess it's going to be kind of complicated, but this whole expression over then basically this is a naught, this is the numerator, over then this whole expression inserted in this location, then the 0 information. And so this is the important part, is that this is going to give us then alpha times 203.2 times 10 times 1.029. Okay, so now what this does, this is an E final here, is a function of just a single alpha. So this is our gain that we can tune. It tells us what alpha should be if we want to hit a certain performance specification. So the way in which we parameterize this, t dropped out, right? So in this, t is always multiplied by s. So when we evaluate that as s equal to 0, that term has no effect on the system, right? So we can say that now E final can be written as a bunch of constants and just this alpha term. And if you were to plug this into a calculator, you would get 444.85 over alpha times 2091 plus 444.85. All right. And we want this E final to be less than 1%, right? 0.01. Yes?
Why does the alpha in the numerator cancel because that transient response completely back control?
So the alpha in the numerator does not go away. So the alpha, so keep in mind that this is written as B over A. Is a standard form. So the A terms do not have an alpha because it's alpha TS, right? And we're evaluating S is equal to 0, so that kills the alpha in the denominator. The alpha in the numerator is alpha times the quantity TS plus 1. So the 1 multiplied by TS goes away, but the 1 multiplied by 1 persists. Does that make sense? Okay. Okay. So we're going to multiply this out and evaluate by 0, right? So this term goes away, but then this is alpha times that quantity. So alpha times 1 still remains. This S goes away, this S goes away. Yes?
So previously when we did like the final value theorem, we all had this like limit of s times the transfer function as s goes to 0. Is that just because we're dealing with the time domain and now we're dealing with the
So yes, if you go back to lecture 12, you'll see that this equation here, this E final is equal to A naught over quantity A naught plus B. This leverages final value theorem. So the final value theorem is actually already baked into this equation here. All right, so we need to find alpha such that this is true. And so this is, as we can see here, if we want the left-hand side to go down, right, we want alpha to go up, because alpha's in the denominator. All right, so larger gain is going to give you a smaller E final. You can solve this with your calculator, but you're going to get that alpha should be greater than 21. And so in terms of a design, we have to pick a design. We can't put something greater than something in the design for an actual controller, so we just say alpha is equals 22 for good measure. Okay, so we're picking an alpha such that the steady state value is going to be adequate or meet our specifications. Any questions on that analysis in terms of trying to find that value? Okay. All right, so this next one we won't quite get through this. Maybe we will. We have 5 minutes left. All right, so design T such that the lag controller has little or no effect on stability and transient response. So let's do just a little bit of a thought experiment here. All right, so we have our lag controller such that, okay, so the lag controller, our poles and zeros are such that our pole is smaller than our 0. All right, and so in this example, it's actually 22 times smaller than our 0 location, right? Because alpha is equal to 22, and that's the ratio between them. So if we say that it's kind of if this is 1 unit, this is then alpha units. All right, so 22 times far away is our 0. And we know from our discussion of the lead controllers, root locus, etc., that the root locus is defined by this angle criteria, such that a value of S, for this to be on the root locus, it has to satisfy this angle criteria that the sum of all the zeros minus the sum of all the angles from the zeros to that position minus the sum of all the angles from all the poles to that position has to equal 180 degrees. And so by putting in a pole and a 0, such these are in these locations, this is going to definitely throw off that angle criteria. Because if I look at this angle from my 0 and this angle from my pole, these are angles that are nowhere near each other, right? They're probably 35 degrees off. Right? So that's what defines our root locus. So we're saying that the transient response is defined by the root locus plot. What we're doing here is we're trying to make sure that the root locus plot is not appreciably changed. It will change some, but we don't want to change it much. All right, so how do I make sure that these angles from my added lag controller basically are approximately the same, so that the 0 angle cancels out the pole angle? How do I make sure those are essentially the same angle while also having the 0 being 22 times as large as the pole? How would you do that? Where should I place that? Any thoughts on that? Carson? In the middle. What do you mean by in the middle?
So the 0, equal distance from 0 to the point from S to point to X.
Okay. So you're saying somewhere here, right? I drew that poorly, but somewhere here. Okay. But we need the 0 to be 22 times as large as the pole. Yes.
To the left of the 0, so that way both angles are -180.
Okay. Negative 180 to the left of the 0. What do you mean? So way out here?
Yeah.
Okay. So that's actually one way. So you have to either put them way, way, way to the left, such that you have a pole location that's a, negative 200 and then 22 times negative 200, right? So that will not distort distort your response at all. Because it's so far out to the left, and then the angles are going to be approximately the same because they're all going to be really small angles. But that's actually going to have, we can go into the details of why that, it's going to, well, yeah, that's not the right answer, it's the other answer. So what's the other option then? If you want to have the same idea, you want the angles to be almost identical to each other, but also have one be 22 times larger than the other one. Really close to the origin is the other way to do this. So yeah, the left, all the way to the left works in terms of angles. What we're going to be doing is, if we're really close, oops. Okay, so if we're really close to the origin, I have my pole here, very close to the origin, and my zero is right here. I can still make these 22 times as large, the zero is 22 times as large, but the angles coming from each of these are approximately the same. So if I were to say zoom in to this location, and say redraw these axes, so one is still, in terms of multiples of each other, can still be larger than the other one, but it's not going to affect the root locus plot at all, or very minimally. Yes?
Will those kind of like cancel each other out because they're so like small numbers, or like because it's so close to zero, it's going to have a dominating effect if we don't?
Okay, so that's the next point. So if we look at other root locus rules that we've drawn, right? So we know that what we're putting is we're putting a zero and a pole really close to the origin, which is going to be probably away from all the dynamics of the plant itself. And so in terms of the root locus plotting techniques, right? So we know that on the real axis, the root locus is between, to the left of an odd number of poles and zeros. So we're going to have a branch of the root locus of the system that's here. Right? And so what that means, the closed loop pole for some sort of gain of k is going to be, say, here. Right? And so you're going to get an effective pole zero cancellation as well from this. So even though you may have a pole really close to the origin, which if we go back to our previous notes, say it's going to cause all these other negative consequences, it's going to be nullified by that zero. All right. So I actually went a minute over. We'll finish up this example on Wednesday, but that's going to be our basic strategy for designing T. See you on Wednesday.